Okay, so we are going to start the tutorial 3 for CO224, and now today we'll be continuing with the rest of the chapter 2, which is about the instructions or the language of the computer. Yeah, we are talking about ARM instructions, and the contents or the content that we'll be looking at today is given here. Uh, so today we'll be looking at something new, uh, which is about function calling. Function calling, I think you all have looked at how you can call a function and uh, return a value from a function and things like that. You have seen how you can do them in high level languages like C, but in assembly you have not looked at them yet. So today we'll be looking at function calling, and we'll be looking at a few function calling examples, and also the memory layout in computers. That also we'll discuss, because that is also going to be important when it comes to function calling. So that is the content. And first we'll look at how you can do this function calling. For function calling, there are several steps involved or required, and these steps, I'll go through them. Like I'll just mention the steps that you need to do, and then we'll look at how you can actually do them with an example. Otherwise, it will not be very clear to you all. So just like for now, just uh, get to know the basic steps only, but like we'll see how they can be applied in practice later, like so. The first step you have to do is to place parameters in registers. Now you all know how, like, you have to, when you are calling a function, the typical case is you pass parameters to functions, and that in assembly is achieved by placing parameters in registers, because in assembly the only thing you have is registers to hold, like for variables or anything like that. The only thing you have is registers, so you have to place the parameters as well in registers. And then the second step is transfer control to the callee function. Callee and caller, those two terms also you should know. Caller is like the function that calls the function. That is, could be a function, the main function, or anything like that. So the caller is the one that calls a function, and the function that is called, we call it the callee. Callee basically is the function that is being called. So you have to transfer the control to the callee function, and then you need to acquire something called stack storage. So that also we'll look at. So you have to acquire stack storage, and then as the fourth step, you have to backup registers. That also we'll do. So then as the fifth step, you have to do you have to perform functions operations. That is like the core of the function, where you perform the functions operations, and then you place the result in register for caller. So the return value also you have to take that using a register. And seventh step is restoring the registers that you backed up earlier, and then finally return to place of call. So that is the final step of function calling. And when you are doing this, to do this, or when you are doing this, you need to have a convention. That is, so that also it will be more clear when we go into the example and discuss about how it works, how function calling works. So we have to have certain conventions. So in ARM, we have this ARM register conventions. Maybe we'll come back to this slide when we get the real need of having such convention. So there are conventions like these registers, we'll be using them to this purpose, for this purpose, and in these registers we'll use them to for this purpose. So that type of a convention we have. That's a convention. So you all know, I think, what conventions are. So those are rules that are set by us. So you can do it in another way, but the convention is this. So everybody should ideally follow these conventions. So 0 to 1, or the first two registers, we use them to place arguments. Now we talked about, like, you all know what function arguments are. So for placing the arguments, we use these registers from 0 to 1. Actually 0 to 3 we use to place arguments. Now both these column rows say that you can put arguments in 0 to 1 and 2 to 3, and also 0 to 1 you can use it to return the result, and also it can be used as a scratch register. And 4 to 11 we use them to store variables for local routine, and 12 we use it for intra-procedure call as the intra-procedure call scratch register. This one maybe you don't need to worry too much. And then these final three registers, like the last three registers, we already asked you, like, can you all remember now when you were trying to use these R13, R14 and R15, you encountered a problem. So some of you encountered a problem, like you were getting error messages that there's a stack overflow happening. So things like that you encountered because you were using these registers. And that is because these last three registers are used for these special functionalities. And so this is the convention. So they are just like normal registers, but the convention says that you have to use them for a certain special functionality. For example, this 13th register, we use it as the stack pointer. So stack point also we'll discuss about it in later. We'll discuss about that also. And this 14th register, we use it as the link register, where we'll be storing the return address actually. And this 15th register, it is used as the program counter. Now program counter, you all know, program counter tells the next instruction to be executed. Actually, when you look at the program counter now, what it says is the next instruction that the processor should execute. And so it is like keeping track of your program, the current location of the program that is being executed. So this is like the convention. So these three registers, we didn't look at them officially or like formally earlier, but here you will get to use them. And there's another field here, column, saying whether you need to preserve these registers on call or not. So this concept also, it will be clear when we actually look at the example. So convention is you don't need to preserve these first 4 registers, 0 to 3. You don't need to preserve them when you're inside a function, and then 4 to 11 you have to preserve, and then this one you don't need to preserve. So there's something like that, but what actually preserving means, we'll look at it like soon. And so far, do you have any questions? Like, we were anyway briefly looking at the concepts that are needed, but here we are going to look at a real example where we call a function and how it can be handled in assembly. Hope you all are following, and if you get into any issues or doubts, just let me know, right? And now we are going to look at function call instructions. Now, one thing you need to notice is that, like, there's no special kind of like you don't have a special instruction that says function call. Something like that is not there, but there are certain instructions that are there to facilitate function calling. One such instruction is this BL instruction, branch and link instruction. So that is something you will be using only with, most probably only with function calling, and this is a special function, special instruction. And apart from that, you will be using just like a usual instruction that you already have looked at, this move instruction. This also move PCLR actually. This instruction also you will be frequently using this, and you actually have to use it when you are returning from a function. So these are just basic instructions. That is the thing you need to notice. Like even in conditional operations, we saw that it is just about branch into a certain address and then coming back, like jump into another location, the programs or those things. So you don't have things like if, else. So those keywords are not available in assembly. You have to use the basic operations that can be done with a real hardware element to perform all these high level, or to achieve all these high level constructs. For example, for if else conditions and also for loop conditions, we had to use the same branch instructions. You did not have a separate instruction for loops, and you did not have a separate instructions for if. So the same instruction, the same concepts you had to use. You had to use for those two concepts, and here also the branching concept you have to use here as well. So because we are looking at things at things that happens at the lowest level. So the first instruction that you'll be dealing with is BL instruction, where you use like which will be used to call a function. And maybe we'll look at it with the example, and then you will be able to understand it better. Now, for that, I'm going to use to demonstrate this example, I'm going to use the visual tool that you all were introduced to. I hope you all have tried to at least install the tool and try to do something with it. By the way, did you all see that I had posted a notice about the tool? It's an interesting tool actually. Did anybody try using the visual tool? Is anybody there? Anyway, I'm not getting any response. Okay, yeah, seems like some people have, maybe one person has tried it. Yes, and if you have not tried it yet, then now this is maybe the best place where you can use it, because when it comes to things like function calling and handling stack and things like that, you will be easy, like it will be easy for you to understand how things happen with a simulation tool like visual, because it simulates how things happen, like how a register, like now we all say, like we are saying that we are assigning values to registers, and then we are branching to certain locations in your program, and your program counter is going to hold the address that the processor is going to execute next, and things like that we are telling, and those things are actually happening under the hood, but you are not seeing how those registers are updated and things like that. You are not visually seeing them, how the status of all the registers and things like that. So this tool, you can use it for that purpose, to simulate or see how things happen. And can you all see the screen? Maybe I'm sharing only the PDF. Yes. So I have an example code loaded into the visual tool. Can you see my screen? Like visual tools screen?
Yes, sir.
Hope you all can see because I'm changing the screen. Can you see some code printed on visual? Yeah, good. Okay, so this is actually the visual tool if you have not looked at it yet. So this is the tool, and then this sidebar is there to show you the status of each of the registers that we have in the processor, and it says what is the current value that is being stored there, and here you can write your assembly code. And then the good thing is that you can execute instructions step by step. Now this one here is step forwards. So you have these options. Now at the rightmost, like top right, you have these control buttons, and when you click on this step forwards button, it executes one instruction, and when you click on it again, then it goes to the next instruction, and it executes that instruction, and the registers are updated accordingly. So you can see how content in the registers change. And also the register content, you can see it in decimal, binary, hexadecimal. All these number formats also are available. So now the first thing we did was loading 10, the value 10 into R naught register, and you can look at, like, you can monitor it in hexadecimal format and also in binary and also in decimal. So if you put it to decimal, you can see it's loaded with 10, value 10, and then R1 is loaded with value 5. And now what are you doing in functions actually? Now I'm going to the step where we are actually trying to call a function. Now in functions, what we actually try to do is to execute a code segment that is written separately to the main code, and we need to execute that code segment, right? Now we can actually do that using these labels, same labels we looked at earlier with when it came to the control operations. So here also you will be making use of labels, and now say here you have some code in the main function, and you are doing certain things in the main code, and then you get the need of calling a function. And for that, a simple instruction now you can think of is this branch instruction, right? Now first you have the function defined in somewhere in your code, starting with a certain label. Now this part is my function, and this function, what it does is it does this operation, a plus b minus 3. So this function I have written it to perform this a plus b minus 3 operation, and I have named that function I have named it with this label func, right? So now with functions, what we need to do is to go and execute a certain code segment that we have defined in our code, right? So function, we have already defined it somewhere else. Now we can actually use this branch instruction to branch to this location in the program, so that it will go and execute whatever is there at that location, starting from that location. So this is a good way of executing a code segment that we have written separately to the main code. Now if you do this only, we'll run this, we'll simulate this one and see. So the first thing we are doing is moving 10 to R0 and then moving 5 to R1, and then we branch to this function. Now what this function does is, now we branch to this one, and what it does here is it takes the value in R0 and R1 and it adds those two values and put it back to R0, right? Now with this, we can actually do this A plus B thing. And the parameter, so another thing that is happening here at the same time is I'm passing parameters to this function. Can you all see that? So with this, actually at the start of this code, what I'm actually doing is passing parameters to this function, because function is a code segment that is written somewhere else, and you have to pass parameters. These A and B, for example, like in this example, A and B are the two arguments that I need to pass to this function, and I'm passing those arguments again using registers, because the only thing you have in assembly is the registers, like I mentioned earlier as well. So to pass arguments and also to do your like general calculations, and also to store the location in your program that is currently being executed, to all these to do all these things, the only thing you have is the registers to maintain the status. The only thing you have is these 16 registers, and also you have the status register that is also there, and certain other registers. But the most important thing, like the most frequently used thing, or the main thing that you have in the processor to store all these things, is this set of registers R0 to R15. So we are passing arguments as well using R0, the registers, usual registers. Now in this case, I'm using this R0 and R1 to pass this A and B values to this register, right? Now with the add instruction, what I'm doing is adding these two values, and if you step forward, I'm subtracting this constant 3 from the addition A plus B, R0 minus 3, right? Hope you are following. Now R0 is like initially it was loaded to 10 and 5 that we actually looked at earlier, and now R0 contains the value of A plus B minus 3, that is 10 plus 5 is 15, 15 minus 3 is 12. So R0 contains the value after you perform this operation A plus B minus 3. Okay, are you all okay with up to now? So there's nothing not to be okay, right, about this part. Are you okay? So I'm using this tool. That is the only difference, right? Yeah. Yes. So okay, good. So we are done up to this point, and then we try to step it forward, step it forward further. Now in functions, what happens usually, or what should actually happen is, once you call the function, it should execute the code segment that is defined inside the function, and also the next thing, the next immediate, like once it is done with the function execution, the next immediate thing that should happen is it should come back to the place where the function was called, right? That is how functions usually work, right? In C, you have seen that is something you expect the program to do. When you call a function, it should go and execute the code written inside the function, and it should come back to the place it was called. The function was called, actually, place meaning that starting from the next instruction, it should start executing the rest of your program, right? But with this method, like if you use just bfunc, can you come back to this place where the function was called? Can you come back? When you have this, just this branch function thing, it will branch to this location and it will execute these instructions, and there's no instruction asking the processor to come back to this place. Actually, this is the instruction that we use to call the function, and after the function is called, we are expecting the program to continue its execution starting from the immediate next instruction. That is these two instructions. So these are some other instructions that the instructions that we should execute, that should get executed after the function call. So these are not things that are inside the function anyway. So these are the things that it is like the rest of your program, rest of your main program. So this is the main program. Initially, you are assigning values to certain registers and you are calling the function, and you are expecting the program to come back to this place. Now with this implementation, can you come back? Or you can. Do you think you can come back with this? No, yeah, you can't, right? It's better if you can respond quickly so that we can like move forward quickly. I'm trying to do these things slowly, because if I go quickly and like cover it up within maybe 10 minutes, like I can actually do this slide within maybe 2 minutes. But if you don't get the idea properly, then it will be hard for you to go ahead with the rest of the examples, because the real applications of functions, they are going to be complex. So you cannot, right? So to do that, we need to have a method to come back to this place. Now this is where things get interesting. Okay, if you want to modify the code, you have to reset this whole thing is in this reset button. If you didn't know how to do that with the tool. So we are done with the operation. Like we could actually get the thing defined in the function done, but we could not come back to the place the function was called. Now for this, we need to use, that is why we are going to use this BL instruction. So in the slides, you saw that we are going to use this particular the special instruction called BL to do function calling. Now BL, what it does is, actually BL stands for branch and link. So branch and link, what it does is it calls, or it jumps to the label defined in our program, and like that is just a usual branch you already have seen. So you branch to that location, and also it updates a special register in the register file. So now if you want to come back to this location after the function call, you need to remember this place, right? That is, you have to store the place, the location in the program that you should come back or return. So for that, actually what you should actually remember or store is the address of the next instruction that should get executed after the function call, right? Because after you're done with these two instructions, or the instructions that are inside the function, once you're done with all these instructions, the next immediate instruction that you should execute is this instruction, right? The instruction after the BL instruction. So in this example, this LSL instruction. Now what BL does is, in addition to branch into this instruction, it updates this R14 register, or in other words, we call it the link register. It updates this link register with the address of the instruction that is next to this branch instruction, BL instruction. So that is the next instruction that we should execute after the function call. So here in this example, we have only like 1, 2, 3, 4 instructions. So the location of this instruction is going to be 1, 2, 3, 3 into 4. That is 12, because each of these instructions are going to take 4 bytes in memory. So we all know that memory is byte addressable. So in the instruction memory, to store this instruction, you will need 4 bytes. And so this, of course, will start from 0th location in the memory. And this instruction will be stored starting from 4th location in the memory. That is because one instruction takes 4 bytes in the memory. So 0, 1, 2, 3 bytes will be used by this first instruction, and 4, 5, 6, 7 bytes will be used by 4, 5, 6, 7 locations. Those locations will be used by this second instruction, and the third instruction will take 8, 9, 10, 11 locations in the memory, and this one will be stored starting from the 12th location in the memory, because we are going to address each byte. We already have looked at this. Each byte in memory, we are giving a unique address. So 12 is the location in the instruction memory that stores this instruction. So we should come and execute starting from 12th location in the memory. So we should update the link register with the address of this immediate next instruction. So we should update this value with 12. So this is exactly what this BL instruction does. In addition to branch into this one, before branch into that instruction, it updates this link register with the immediately next instruction's location. So it will update this LR with value 12. Now, if you run it again, if you execute this program again, you can see now as soon as you perform, we are currently executing this BL func instruction. The instruction that is highlighted in yellow is the one that is getting executed currently. And if you look at the LR register, now you can see it is loaded with the value 12. So this is exactly what we were expecting it to do. So before branch into this one, it updates this one with 12, value 12. Now it's done, and we step forward. Now we know the exact location that we should come back. So now it executes the instructions inside the function, and now we try to step forward, but it does not step forward, because do we have any instruction asking the processor to come back? Now we have stored the value, the place in the instruction memory where we should come back. We have stored the location, but are we instructing the processor to come back yet? No, right? No, we are not instructing the processor to come back. We have stored the location where we should come back. If somebody is not clear about anything that we are discussing right now, just let me know. Just interrupt me at any time, because if you don't know the basics, then it's going to be hard. So we need to have another instruction asking the processor to come back. So that instruction will be this instruction that I'm going to write here. What if you do this? Move PCLR. Now PC, what it holds is the next instruction that the processor should execute. And the processor actually looks at this PC. When it tries to execute a new instruction, all what it does is it looks at this PC value, and it fetches the instruction located in the location point like specified by the PC. So PC holds uh, the, 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 the location of the next instruction to be executed. So that idea we already have. If you don't have that idea, then that also you can just like let me know so that I can talk about that also, maybe like a little bit about that also. So PC is holding the next instruction to be executed. Now link register or this R14 register is containing the address, the location of the instruction that we should come back. And after this functions operation, what we are doing is we are asking to move the value in LR to PC. So this will what it will do is it loads the PC with the value in LR. So after you are done with this instruction, at the next clock, at the next clock edge, what the processor does is it go and checks the PC value, and program count value it checks, and it goes to that location in the instruction memory and starts executing from there. Right? So that is the whole purpose of the PC. Like PC is there to tell the processor the instruction that should get executed next. So if we change the PC so that it executes this next instruction we want to get executed, then it's going to do the job that we need to do. Understood? Did you understand what we did here? Move PCLR. Maybe we'll execute the instructions and see how it works. So we are loading R0, R1 with these values, and we are branching to this one. And this is the place we are currently at. And these things are there to just let you know that these things are updated to these particular locations. So you should keep your eye on the line that is highlighted in yellow. So this one we are executing now. So R0 and R1 are the only things that are updated, and also the LR. Maybe we'll put them to decimal so that we can see them clearly. PC is currently holding this one. And now we are done with this. And PC LR. 1, 2, 3, 4. It should actually assign the value of LR into it. It should put the value in LR to PC, and that is how you should come. You will be coming back to this location. For some reason, it's we'll see. I'm seeing some unexpected behavior here. That is why I'm trying to. Oh, what's that happening there? something funny happening here. When you reset and start executing the code, maybe that is happening because of a certain standard defined here in this program or something like that. The PC is initialized to 8. Actually, when you are executing this instruction, what it should store or hold is the value of the or the location of the instruction that should get executed next, which is actually 4 here in this case, but for some reason it's getting assigned the value 8. Anybody having any idea about why it happens so? If you have worked with this tool before and tried to find a reason. Now see here this yes, seems like it starts the first instruction is put to the location 4 in the memory instruction memory, and it's not started from 0th location in memory for some reason, and this is anywhere tool developed by a like a university, not at all developed by ARM, but it's really a nice tool that you can use to simulate how things happen. But seems like the first instruction is put to the 4th location in memory, so it starts executing from there. And here you can see now when you come to this location and the PC is updated with value 20. So that is where it should come, and PC, the LR is 12. Now you need to load PC with the LR, and it's updating it with LR plus 8, depending on the way this emulator and how it internally works. Okay, we'll go back to our example, and the idea you need to have is this one, the one I was discussing about. But after you execute these 2 instructions in the function, you should move the value in LR to PC, and that value should ideally be the value in this 12 the LR register, and like in order for this system to get back to this location, it should update the value with LR plus 8. So that is how it will be able to come back to this place. So that plus 8 offset is coming from the internal implementation. Anyway, it knows now, since we have stored the place that we should come back in LR, it can do, like, it can perform any offsetting it needs to do and come back to the place. So the main idea here is to have a method of storing like storing a hint to come back. So we have stored that hint as 12 here, but when it assigns this value in LR to PC, it performs this plus 8 thing as well. So plus 4 is making sense because usually PC is updating its value by 4, like it's incrementing its value by 4 in after every instruction execution. If it was assigned PC plus 4, something like where we were earlier, can remember. 36 and 20. So you can see anyway the earlier value was 36. So it was trying to execute this one. Yeah, that's okay. So 36. So the instruction corresponding to that 36th location is this one. And it executes this. And if we did not have this move instruction, that is, if we don't have an instruction to change the PC value, it would update PC with this 36 plus 4, that is 40. But instead of 40, we are signing PC with, or loading PC with this 20 value. So when you do that, if you run the simulation further, you can see now it comes back to this place, right? So depending on your internal implementation, there could be an offset, because how you fetch the instruction memory, and how you have the logic for PC and things like that, maybe depending on that. The basic idea here is you update the PC with the current value in link register. So link register is going to store the instruction, the location in the instruction memory, where you should come back after the function execution. And after the function execution, so after you are done with functions operations, you move the LR into PC so that it can come back to this place. So it will go and execute the rest of your code. So the main concept we are using here, I think it's clear to you all. The offset thing, you can ignore it for now. That is some internal stuff, but the main idea here is you store the place you should come back in LR, and you move that value to PC. So when you do that, you can your PC gets updated with the location that you should come back, and then it starts executing from the immediate next instruction. Hope that the basic idea is clear. Now, if you go forward with, okay, somebody's raising hand. Any questions? No. Okay, so step forward. If you step forward further, it will go and execute the instructions that are just after the end of your program. But the assembly program does not know that it is the end of the program. All what it can do is all what it will do is it executes instructions that are they are in your program one after the other. If you don't have a branch instruction, you are going to execute instructions one by one. And here the same thing happens. Since we don't want this function to get executed again, just like after you are done with all the things in your program, you don't want all the functions defined after, like below your program, to get executed. So to avoid that situation, you can have an instruction like this: branch exit. And so with this branch, what you are doing is you ask the program to branch to this exit location where it is. It will be the end of your code. So you can implement that in any way you want. Like if you wanted to have the function definition at the function, or the function definitions at the beginning of your program, then you will have to have a method to branch to the main function first, and then do the function declarations accordingly. Are you clear with this idea? So this offset thing, I'll look into it and see, like if they have the reason and all that in the documentation, and also the ARMS implementation. I'll go check it and let you know if there's a good reason, or there should be a good reason. If it is explained anywhere, I will let you know. But the basic idea, did you get that? So why we are doing the BL and move PCLR instructions? Clear? Okay, good. Yes, that is good. So with this simulation software, actually, it's really you can simulate things very nicely. Otherwise, if you had only the instruction, then it's hard for me to explain it and also for you to understand. So we are done with the simple example. And now we can go back to our slides and see. So you can see my slides, right? Yes. So these are the two instructions that we use to do the function calling. So function call, the first one is branch and link, BL function address. So function address is actually the label that that is given to the function. And address of the following instruction put in LR, so that we saw the address of the instruction that comes immediately after this PL instruction. We put it to LR, link register, or R40. And then we jump to the target address. That is, we jumped into func location in our program, in our example. And then to return from the function, you have to do this instruction where you move the value in LR to PC, copies LR to program counter. Then when you continue, when the program continues, it will go back to the place where we called the function, right? So that is about it. So the basics we now have discussed, and this one is a example C code for an example function. And here you can see this one. It is doing like basic operations. It's doing adding two values and subtracting this addition from that one. And you can see here something special, like something new mentioned. The arguments GHIJ. Now arguments, we talked about that. Now these things also we'll discuss with the same example we used, right? That will be better. Now these arguments, now you have seen the how you pass arguments in C, GH and GHI and J. These are the four arguments that are being sent to this function, and those things you can put in these R0, R1, R2, R3 registers. Before you perform that BL instruction, you have to put these values in these registers so that they can be used by the function, because all the whole code in your program, it has this shared 16 registers only. So when you call a function, or when you go actually what happens is you branch to a certain location in your program when you are calling a function in assembly. When you go there, you are not going to get a separate set of registers. So you have to use the same 16 registers to do all what you are doing in your program. So passing arguments is also done using the same set of registers you have here. Here we are using these R0 to R3 registers for passing the arguments. Now this is actually what it was mentioned in this register conventions. Can you see this 0 to 1 and 2 to 3? We have this the usage of these two or these four instructions. What it mentions is you can use them to pass argument. That is why you are having the usage as argument. So the convention is to use these four registers to pass arguments to functions. So you are loading these four registers with the arguments you need to pass to the function. And the other thing is return result. You can see here for 0 to 1 registers, we are having a usage return result. Now here in the example, we saw that R0 and R1 were assigned with these values so that they will be passed to this function. And finally, the return result, or a plus b minus 3 value also we are putting to this R0 register, into this R0 register. Now, whatever is there after the function call, the rest of your program, it can refer to the return value if you pass it to a register only. Like if you load it into a register only. So after this operation, like now after this sub operation, you are loading like when you are done with the function, actually R0 is loaded with the a plus b minus 3 value. So that is actually the return value. The return value of the function, we are expecting it to assign this calculation into some place in your processor. So that some place is this R0. So R0 into R0, we are going to put the return value actually. Now, the rest of the code you have here in the program, it can read R0 to get to know the return value. Now in C, you have seen you are assigning the return value to another variable. So things like that happens in C. But when it comes to assembly, all what it can use to get to know about return results, arguments, and all that, for all that you have to use these registers. So we are assigning the return value to this R0 register. So we have to have a convention. That is the reason why we need to have a convention, because the rest of the code, it needs to know where the processor will be putting the return result. Otherwise, it cannot know, like, I mean, all these registers are the same. So it needs to know beforehand what is the register that I need to read in order to get the return value of the function that I called. So that register is this R0. So we are having this convention. So whenever somebody writes a function, he or she needs to put the return result into this R0 register. So you all know that you are using some library functions, right? So when it comes to C and other programming languages, you are frequently using library functions. So these functions actually are not written by us then. So there should be a convention. That is why we need to have a convention. Now, if we are if you are writing the whole program, including all the functions you are using, then you can have your own convention. I'm loading my return value to R5, something like that. And then when you want to read the return value, you can read that R5 register to get the return value. That you can do if you are the only one writing the whole code in your program. But if it is not the case, if you are using library functions and all other stuff, and also if you want other person also to be able to understand your code, you have to have a convention. So this is the register convention. We are using these R0 to R1 registers to get the return result. So typically, since we, like in C, you have seen we only are able to return a single value. So we will be using only R0 to get the return value. So that is why we have in the convention that R0 to R1 should be used for can be used for return to store the return result, and also they can be used as scratch registers, that is to perform your immediate calculations. So these are the usages. Now R4 to R11, these things you can use them to perform operations inside your local routine. That is, you can use them as variables for local routine. But if you are going to use them, one thing you need to do is, one important thing that you need to do is you should preserve them. So this is why we have this column. If when you are using these registers inside a function, I'm talking about a function actually. If you are inside a function, so your function has been called now by the caller, by your main program, and you know that these 0 to 3 registers contain the arguments that are passed on to this function, and 4 to 11, they can be used as local variables inside your function. But if you are going to use them you have to preserve them. The reason for this is something like this. Now, all these 16 registers are going to be shared by your program, your full program. And let me load another program. Now, if you look at this program, this is actually the compiled code for the example that we saw just a little while ago, like the G plus H minus I plus J thing. So there we wanted to use these 4 registers to pass the arguments to the function. So that function we had called it example, and we are branching to that location. Now, the R4 to R11 registers, the purpose of preserving R4 to R11 registers, that is what I'm trying to discuss here. Now, since all these registers are shared by your code, now say for example, you have been using R5 register. This is an example. R0 to R3, you can of course use them to pass the arguments. And inside your main code, you were using R5 for something else. Now, for in this example, R5 was holding this value 5, right? So we were using this R5 to hold this constant value 5. Now, when you come to this point and when you branch to the function, you go inside the function, and if you like if you used this R5 without preserving or something like that, if you uh, without storing R5 in somewhere else, what will happen is you can, inside the function, you can replace the value stored in R5. But when it comes to function calling, the program does not know about that. Like it is not expecting R5 to be altered by the function. That is why we have preserved on call as yes on the convention, in the convention. So that is how we have defined the convention. R4 to R11, those registers, we are expecting them to be preserved by the function. That is, when we come back after the function call, we are expecting R5 to hold the value it was holding before you called the function. That is, when you come to this point after the function call, you are expecting R5 to hold the value 5. So your function cannot alter the status of these registers R4 to R11. If you get the need of changes in the state of those registers, you need to make sure that when you come back, when you go back, like when you return from your function, you need to make sure that these particular registers, you need to make sure that they are loaded with the values that they were holding when the function was called. So this is the key idea here. Was it clear? R4 to R11, we are telling we should preserve, like they are preserved on call. That is, when you call the function, we are expecting the main program, actually the caller expecting them not to be altered by the function. So R4 to R11, those registers should hold the values that they were holding before the function was called. So when it comes to this point, it is expecting R5 to hold the value we had just like before the example function call. So the only things that can get altered by the function are these R0 to R3 registers. So R0 to R3 registers, we are not expecting them to be preserved by the Coley function. So we are like actually R0, we are expecting it to contain the return value. So that is something. And these other registers R0, R1, R2, R3, these registers, we are not expecting them to be preserved. So if you want them to be preserved, like if you want to have them hold the values, or in other words, if you want to preserve these values in these four registers, you have to preserve them inside the main code. Maybe if this is something like, if it is complex, maybe you can ignore that for now. The only thing that you should focus is that if you are using R4 to R11 inside your function, you need to have a mechanism to preserve them. Of course, you will get the need of using all these registers, because with only these four registers, you might not be able to perform all your calculations inside a function. So of course you will get the need of, because this is actually a small example, but when it comes to large functions, you have seen large functions. So when it comes to something like a C sort, like, I mean, the sort function, so something like that is going to contain a lot of code that will need a lot of registers. So if it is the case, you have to use these R5 to R4 to R11 registers inside the function. So if you are going to use them, you have to have a way of preserving them. So that way we call it preserving them in the stack. So that is where we should go next. So now actually what I discussed was the need of preserving registers, because we have the convention that those values in these registers R4 to R11, we are expecting them to be preserved by the function. Did you all get that idea anyway? If it was not the case, then there's actually no point in describing the rest. Maybe it will be more clear when you go into examples as well. So I was trying to describe the reason why they have been labeled as preserved on call. Right here we have saying that R4 to R11 are preserved on call, so they have to be preserved. So we'll now in this example, you can see that. Now focus on this example first, and maybe if it is not clear, if that what I was discussing was not clear, you can see how it works with this example. So example function, inside this one, you have to perform this calculation. Now to perform this calculation, R0, R1, R2, R3 are going to hold the values of the arguments passed on to this function. So you cannot maybe use these same registers to do the calculation, this calculation. So you get the need of using another register, something like R4. Yeah. So you get the need of using R4 to perform this calculation. But the convention is, we have a restriction. Like in the convention, we have a restriction that if you are going to use R4, you have to preserve it, so that when the function returns, it will have the value that was there before the function was called. So then we need to save original value of R4 on something called this stack. So this stack is nothing but it's a place in memory where you will be using to store these kind of values, temporary values. It's actually temporary storage in memory. It's a conceptual, like it's a portion in memory that is used to store these kind of temporary things. So what you can do here is, if you get the need of using R4 inside your function, what you can do is you can actually put the current value of R4, you can put it in the memory, right? We know there's another storage element we have is the memory. So when we ran out of registers, what we were doing was putting those values in the memory, and we looked at how you can store array values in registers and how you can get the values from arrays and load it into registers. All these things we have discussed. Now when it comes to function calling, we often get the need of preserving these kind of values, and it is not only the register values but the things like LR, linked register value. Those things also we get the need of preserving them. When it comes to things like nested function calls, we'll look at that later, a little later. Uh, so you get the need of preserving these values for like temporarily. So you preserve, when it comes to at the beginning of the function, you preserve these R4 to R11 if you are going to use them inside the function. Preserving meaning you are storing them in the memory, and when just before you return from the function, you load them back to the original locations. That is, you are loading those values that were stored in the memory back to the registers. Got the idea? So R4 we need to get we get the need of preserving them, and what we can do is we store the value in R4 in the memory, and we can now use the R4 register for anything you need inside the function, and we are doing that inside the function. And when now the return result, of course, we know we have to put in R node. So you use maybe as an immediate or like an intermediate variable, you will be using R4. And when you want to return the value, you are assigning that the value of f in R node. You have to put it into R node. Result, you have to put it in R node, and now you need to load the R4 back with the value that it was holding before. Before the function call. So to do that, you can load the value that you stored in the memory into the R4 back. All right. So when you do the example, it will be more clear actually. And you have to have an idea about the stack. So now stack is the place that we are using to storing that we use for storing these temporary values. So R4, R5, R6, these actually here in this example, all these R4, R5, R6 registers, we are going to use them inside the function. So we all know that R4 to R11, we have to preserve them. The place we are going to use to preserve them is called the stack in the memory. So that is it's a conceptual thing in memory, and that how that stack works is it's going to work like this. So this idea also you have to have. Hope you can see the whiteboard. If you understand these basics properly, then it's really easy to get going with the rest of the examples. If you get the idea properly at this stage. So stack is something like this. It's again a place in the memory, and okay. Seems like I can't copy. It's actually something like this, and this is all done inside the main memory we have. So we talked about the main memory in brief, how each location in the memory is addressed and all that. We have already talked about it, and we are going to allocate a certain part in the memory for the stack. That is what we are going to do. And in the stack, we are starting with the highest address location. It's something like this. Now here, let's say it's our memory is 2 to the power 8. And it is starting from the highest address, like it starts from the highest address and goes uh, into locations that are lower than that address. So that is how a stack works, and we'll see how it works. Like we'll see. So stack initially is at the top of your memory. Now you can think of this as the memory, and we all know that each memory location is given a each byte in the memory is given a separate address. Now what I'm drawing here is a full word. Actually, it's not a maybe we'll draw one byte. Yeah, this maybe you can think of this. Yeah, this is a full word, right? So this is a full word. Maybe not. We'll 1 byte. You can think of it as 1 byte, and then we have other bytes next to it. 0xf e. This is the next one. You don't have an option to copy things in the 0fx fd. This is the next location, and right. So these are the two next locations, and this is 0xfc. 0x f p. So these are the locations in your stack and in your memory, and we are going to use it from starting from the highest address for the stack. Right now, say we want to, like, we get the need of storing a value in the stack. Now the first thing that we are doing is instead of going and storing the value in the stack directly, that is like the highest address is 0xff, and the first thing that you need to do is to create space in the stack to store the value we need to store in the stack. Now, for example, we wanted to save R4 in the stack because the main function was expecting the example function to preserve the value. So we get the need of preserving the value and like storing it in the memory, and the place in the memory that we will be using to store that is called stack. And you will see how stack actually facilitates all these things we are doing with functions. The basic idea you need to first know, we need to first create space to store uh, store that R4. Now if it is just only R4, we need only a 4-byte space in memory, right? So 4-byte space you can allocate in the stack. That you can do like that. The first thing you need to do is uh, to create space. That now for that you will need to use these uh, 1 2 3 4, right? These 4 bytes you will need to use to store the value of R4. That is, R4 is going to contain a value of size 4 bytes. So this one you can do. Now I told you need to create space. That is done by reducing this thing called stack pointer. Now we have this special register, other register in the processor that like we saw. There's a special register called stack pointer, right? That was our R13, right? R13 was used as the stack pointer. Stack pointer actually points it holds the value that was put to the stack, that was stored in the stack last. That is the last item, the location of the last item that was put into the stack is stored in the stack pointer. So stack pointer, for example, now at the beginning of your program, the stack pointer is going to hold the value of the current location in stacks, like we call it as like that as well. So the stack pointer first points to this 0xff. 0xff, it's current at the beginning it points to this one. So the stack pointer initially is holding the value of value 0xff. So or the highest address in the memory that is given to the program, or like the highest value in the memory, that is the stack pointer. That is the value that the stack point is going to hold at the beginning of your program. And now when you get the need of storing a value in the stack, the first thing you need to do is you need to decrease this stack pointer. That is actually how you create space in stack. You first need to decrease the stack pointer to this place. You need to decrease it to this place. Now to store the value of R4 in the stack, you first need to create space. That is done by decrementing or decreasing the stack pointer so that it can fill the values, so that it can load memory with the value of R4, value in R4. So that you have to first do. So stack pointer is actually the R13 register in your processor, and to create space for storing one register value in the stack, you need to decrease the stack pointer by 4. And to do that, actually you can perform this sub instruction. You can perform to do that. Just a usual arithmetic operation you are doing here. Nothing too crazy. These are all concepts and conventions we are using. Those are used by all the computers, like most of the processors. So this is how it is done. Now you have stored the we have created space to store this value, and next you can do is this one. the usual store instruction, str. For str, the value, the commands or the arguments that we are giving is this. When you do this to load the stack with a value also, it is just a memory, like it is just a part of the memory, no, that I discussed, no. So that's a part of the memory. So the usual instructions that you use for storing values in memory, we are using here as well. Actually, the arrays you looked at earlier in earlier examples, those also were saved in stack. If you go back and look at your skeleton codes, the skeleton code given to you, you will see that we are doing something with this stack pointer and we are storing values in the stack. All those things were done for you when we gave those things to you, when we gave those skeleton codes to you. So these things were included. So now at the beginning I told you that you will get the chance of understanding all this skeleton code. So step by step you are going to you are reaching that point where you are able to understand the whole code. So the same thing, like the stack, the same stack we are using, the stack actually we are using for this purpose. So you can store R4 in the stack now, and once now you can use R4 for whatever you want inside the function, and you can use R4 to perform an addition, something like this. R0 R1, you want to add the value, do the addition R0 plus R1 and put the result in R4, and now R4 is changed. Now that is done, and now maybe there are other calculations here, right? So there are other calculations. Now at the end, the final result, the final result of the calculation is put to R4 for some reason, and now you need to put it back in R0, because that is the place where we will be using to store the return value R4. So it is assigned to the return register. And now the next thing that we need to do is to get R4 back from memory and load it back in the or load it back into R4 register, right? So that we should do next. We have stored R4 in stack now, and we changed R4, and now we can load R4 back with the value it originally was holding by performing this instruction, right? SP0 stack pointer, like we have not changed the stack pointer anywhere yet. The only instruction that changed the stack pointer, the value of the stack pointer, is this one, sub. Now stack pointer is holding the value 0xfc now, and it has been it was decreased to this value by this sub instruction, and SP is now holding the value, this value. And so when you are loading R4 with this one, it will get the content in memory that is put to here, and R4 is loaded with that. And now the next, another important thing is, once you are done with the stack, like once you are done with the preserving thing, you have to increase the stack pointer. Otherwise, the other function calls or other temporary variables will be decreasing stack pointer from here, and you will not be able to make use of this space again, and it will not be it will be a wastage of memory, and it is going to cause things like stack overflow. Also, maybe you will experience these things as well. So to avoid all that and to release the space, actually, that we call releasing the space that we used, that you have to do, that you can do by incrementing the or increasing the stack pointer by the amount we decreased it with. So we decreased it earlier by 4, and we are now done with the preserving thing, and we increase the stack pointer back to its original value. So this will move to this place now, right? Now we are done with all preserving stuff, and now we can return from our function by doing this one, move PCLR. This is actually the last instruction that you will be having in all your functions. Clear? The real need of using the stack and all that will be clear when you like do the real complex examples as well. And if you want to store multiple values in the stack, you need to create space so that you are able to store all those values. Now, for example, in the example we talked about just a while ago, it wanted to use all R5, R4, R5, R6, all these registers. It wanted to use inside the function. If it is the case, you have to preserve all those registers inside the stack, and when you are going to return from the function, you have to load them back into the original registers, load those registers with their original values when you are going to return. Got it? Or if you need a further clarification, let me know. Now, if another function now needs to store its temporary values, now it can again use this same stack for its operations. It can now stack pointer is the thing that stores, that stores the location of the last item that was put to the stack, that was put onto the stack. When it comes to nested function calls and all that, you will be releasing the stack space only like once you are done with the full call graph or call hierarchy. So that also will be clear when we do the example. So this is the basic idea. So this space in memory is called the stack, and this is actually a last in first out data structure. If you want to look at it as a data structure, this data structure, I think maybe you have seen in C. You implemented it with like you wanted to implement it as a data structure used in a high level language, but this is about the memory, how memory works, for how memory is used to store temporary values, and it is equivalent to the data structure stack. So that is why we are calling it stack as well. If you want to preserve more values, you can go decrease the stack pointer and store the value. And once you are done with the function, you have to load the values back to the registers and increase the stack pointer and release the space and return. Clear? Right. Why did you use this SPSP hash 4? Hash 4 is there because we are actually preserving a 4-byte value, right? We are trying to preserve a value stored in a register. Now, what is the size of the registers we have in our, like each register can store a value of size 4 bytes, right? So we need to, like when we say we want to preserve a register in the stack, we actually want to store a 4-byte value in the memory. Now to do that, we need to create space for storing 4 bytes. Now each location, like each location I have drawn here is like it can only store 1 byte, because we all know a unique address is given to each byte in the memory. That is why we call the memory is byte addressable. So those concepts are still valid because we are still dealing with the memory that we looked at earlier. But this is a special portion in the memory that we are using to store temporary values, but still it is the memory. So if f is one address and fe is the next immediate lower address that you can have for a memory location, and it is also going to store 1 byte. So each location, that each rectangle here is capable of storing only 1 byte. So since we need to store 4 bytes, when we say we want to preserve one register, we need to create space to store 4 bytes in the memory. Clear? If you decrease it with only say 1 value, then you will be able to use only this portion, that is 2 bytes, right? So with 2 bytes, actually you cannot store a 2 or 1 byte. With 1 byte, you cannot actually store a full 4 byte value. Okay, great. After loading into R4, does the stack get cleared? Clearing? No. There's nothing like I mean, there's no circuitry to go and clear the stack. That is putting them all to zeros. Maybe that is why what you mean by clearing. So there's nothing that clears all these bits to zeros. Actually the clearing happens with this stack pointer increase we are doing at the end. Add SPSP hash 4. With this, we are releasing the stack space we used. So a new value uh, can be written back in the same place we used earlier. So that is like overwriting. So the stack will be overwritten by a new value because we are not we don't need to further keep it stored in the stack. So clearing or like that is why I use that term releasing. Stack gets released. The stack space we use gets released, but they are not cleared to zeros because we don't need actually to clear them to zeros. If you are going to clear them to zeros, then it's going to consume more time, more hardware and time and all that. So which is not really needed. Rewriting is the thing that will be happening. Got it? After loading, we are releasing the stack space using this instruction that increments the stack pointer. So it will get incremented. So when another function gets the need of storing something in the stack, it can again decrease the stack pointer and start storing values. Yeah, that is how it works. So I spent a lot of time explaining this one because it is really important. We'll go back to the example. Now you can actually, if you understood all the concepts that I was talking about, then you can easily understand what's given here. So in this example, we need to use R4, R5, R6 registers. All these R4, R5, R6 registers you need to use, and because of that, we need to preserve them in the stack. Now, since we need to preserve 3 values in the stack, we need to decrement it by decrease the stack pointer by 4 into 3. So that is 12. So we are decrementing the decreasing the stack pointer by 12, and then we store all these R4, R5, R6 registers in the stack like this. So stack pointer hash 0 is going to so here in this like R4 has SP hash 0, this thing we discussed already, and hash 4 again, this is a offset. So if you add 4 to stack pointer, it's going to point to the next 4 byte location in the stack. Next meaning that it is within the room we created. Actually, it's not going to use the space that we have not allocated. So we allocate space for 3 registers and we store them inside the stack like this. For 8 we need to use these offsets 4 and 8 to store these other 2 registers, and we are using these R5, R6, R4 to get the result like this particular calculation. We can get it done using these registers, and finally result move to return value register R0. The exact same thing I discussed earlier with like a shorter version of this one. R0, R4, we are putting R4 result back in R0, back in meaning we are putting the result in R0 so that it can be read as the return value by the caller, and we are loading the R4, R5, R6 registers with the values that we stored in the stack. And finally, we are adding the stack point, like incrementing the stack pointer by the same amount we decremented it with, so that the space is released. And finally, we do this move PCLR thing so that it can return to the place where the function was called. Was it clear? This example, is it clear? If it is clear, just let me know. If it is clear, actually, you can continue with the rest easily, I would say. Easily meaning the basic idea you have. Is there anything that is not clear with here in this example? I hope you all are still here and not sleeping. And good that you asked like 2 questions. You should actually ask more questions if you have. If you have any questions, just let me know. Like, it could be a very simple thing, but still you can. Even R4, R5, R6 are not used in the main code. Do we have to do like this? No. Actually, if you are not using them, you don't have to do that. So if you are doing it, when you don't actually use them, then that's going to waste CPU time and space and all that. So you should not, like, you should preserve them only if you are going to use them inside the function. Now, for example, in this one, we are using the R4, R5, R6, we are using them. That is why we are storing. Otherwise, we have to preserve all the values, R4 to R11. They are meant to be preserved in the convention, but we are preserving only the values that we are using here. Good that you are asking all these questions, which means the explanation was okay, and we can move forward. I hope this is the exercise 6 that you can try on your own, and here you have to write this factorial function in the iterative method. You all know factorial because you all done with like past your A-levels with flying colors, so you all know what factorial means, and factorial is there to, like, if factorial n is n into n minus 1 into n minus 2, that thing. So you have to do that with the iterative method. Maybe you have learned how to do this with another way is there called recursion. That I hope that was covered in C. But this is like here you should not use recursion to implement this one. You have to use the iterative method, and you have to compile that code into ARM assembly by yourself. So that you have to do, and this number is passed as an argument. And if you get the need of using R4 to R11 registers, any one of those registers, you have to preserve them. If you don't need to use them, then you don't need to preserve them. Yeah, that is the exercise that you can actually try on your own. And there's a small concept that that we are left with, which is the non-leaf functions. Maybe we'll discuss this as well quickly. Do you have anything after this? Do you have anything? I hope you don't. No. Yeah. Hope it's okay to continue the rest now. Because I think you are not tired actually. I should be the one that is tired because so I'll continue the rest. Otherwise, we'll have to take another slot now since you don't have anything. So non-leaf function. This is about functions that call other functions. Now you all have seen like inside functions, you get the need of calling another function. For now we only looked at functions that are called in the main program, but there are functions that are called inside the function, which is common, right? Now to support nested, now this thing we call it nested calls as well. Inside a function, you call another function. Inside our example function, we call something like another example2 function, and this is called nested calls. And to support nested calls, the caller function needs to save on the stack. Caller function is the function that calls this other function, right? Now in addition, like inside that function, things that it needs in addition to the things that we saw earlier are given here. You have to preserve the return address LR, right? You have to save these things on the stack. Return address LR to the previous caller. That is, if you look at it now when we are calling a function with BL instruction, branch and link, we are updating the link register, right? Now this is the first function that we are calling inside the main program. So we are updating the LR with the immediate next instructions location. And now inside the function, you are going to call another function, right? Inside the function, we are going to call another function, and with like to call another function, we need to again use this BL instruction, branch and link instruction. Now, when you are doing that, when you are performing the branch and link operation, you are again going to update the same link register, because we are not going to have link registers for each and every function we have in the program, because we only have one link register, which is the R13 register we have, right? R14, yeah. So the same link register, we update it again inside the function. Now we are going to lose track of the previous link register value, right? If we are not going to preserve it somewhere else, we will be losing track of that. So now if the leaf function, or the function that is called at the last function that was called, will be able to return to the location that it was called, but the other functions, the functions that are higher in the hierarchy, they'll not be able to return back to their original locations because the LR was updated. So to avoid this situation, or as a countermeasure to this one, or to solve this problem, we have to save the LR as well in the stack. We looked at how you can store values, like store R4 to preserve R4 to R11 in the stack. And now, in addition to that, you have to preserve LR as well in the stack by the caller function. And also any arguments and temporary registers values that will be needed after the nested call. Now say you are inside the first function that was called, and there are certain arguments passed on to that function. If you want to use those arguments after the nested call, you want them as well to preserve. Like you have to preserve them, but that preservation or the saving them in the stack has to be done by the first function. So the function that calls the nested function, the second function. First function is the first function that is called by the main code, and the first function is calling another function, second function. If first function needs the arguments passed on to that after the second function call, it needs to save those arguments as well in the stack. If not, it is going to lose track of all that as well, because for the second function you will be passing arguments with R node. So you will have to modify R node with the arguments that should be passed on to the second function. And if you want to preserve the original arguments, you have to put them back in the stack, the same stack we discussed earlier. And after that, after the second function call is done, restore from the stack after the nested call returns. So the nested call, it can return without any issue. Like LR is updated with the place that the nested call should return. And the first function, when it needs to return to the original location in the main code that it was called, when it needs to do that, it has to restore the link register from the stack, and like it has to load the value of link register to the LR back, and then it can return by using this move PCLR instruction. Was it clear? Was that idea clear? That idea, we are actually trying to look at that idea using like comparatively complex, we can call it. Maybe it depends actually. No, maybe it's not complex, but here we are going to use another like concept in programming. This is called recursion, which I mentioned a little while ago. So recursion, I hope you all have looked at it in your C course. So this nested call thing, we will be looking at it using an example that uses recursion. So the same factorial function, actually, the same factorial function. We like the example 6, I told you all that you need to implement the factorial with the iterative method, and here you need to use recursion. When you are going to use recursion, you all know that you are going to call another function inside some other function. That is in recursion, actually, to be specific, in recursion we are not calling the same function inside the original function. So inside the factorial function, you will be calling factorial back, like you will be calling factorial again with some the arguments, of course, will be different. And for this factorial example, the argument has to be decremented by 1, and it has to call it again. So this is the nested call example we have. And if you want to look at a simple nested call example, then you can have one function and you can call another function that is different from that function. So since we are calling the same function again here, it is going to be an example for compiling a recursive function as well. So argument n, we are putting it in register R node. So factorial, when it comes to the factorial function, the argument is put to register R node, and result, again, you should put it back in R node. So in recursive version of the factorial, what we are doing is, if n is smaller than 1, we return 1, just 1. This is like the base condition in recursion. And if this is not the case, if n is smaller than or equal to 1, we call factorial back. again return n into, and now this original argument n has to be multiplied with the factorial n minus 1. Now here you can see when you are calling the all the concepts that we discussed in this previous slide, you will have to make use of all those concepts here, because any this second point says any arguments and temper register values that will be needed after the nested call, you have to preserve them in the stack. Now in this example, the original argument is n, and if n was smaller than greater than or equal to 1, you will have to execute this line of code, which is going to be the code line that is going to get executed frequently in this example. So you have to get the factorial n minus 1 value into R0 register, and then after you are done with this factorial calling, you have to multiply that value with the original argument n. So now here you get the need of using the argument that was originally passed on to the function after the nested function call. So you will, so what is the thing that you will need to do then, according to the concept the techniques we discussed earlier? One thing is, if you get the need of using R4 to R11, you have to preserve them in the stack. And also, what is the other thing that you will get the need? You will get to store in the stack. Since we are dealing with nested function calls, in addition to, like, if you want to use R4 to R11 inside the function, you need to preserve them in the stack. And the other things that you will need to use, that you will need to store in the stack for this example are link register. That's okay. Yeah, link register, and also what else? N. Yeah, the original value n, or the argument passed on to the onto the function. So that is not always the case. Link register, like for nested calls, it's mandatory. You have to preserve the link register in the stack, but the original argument n, maybe for some functions you will not get the need of using it after the nested function call. If that is the case, you don't need to preserve it in the stack. You need to preserve only if it is really needed. And this is the compiled version of that code, and you can see here fact is our function. So can you all have a look at it and try to understand? I'll give you some time to look at it, have a look at it. And I would call this like this most probably will be the most complex version of nested calls that you will encounter. There could be, like, if you have like maybe it's given as an assignment, or the lab assignment, one of the exercises, I think, if you have recursion with 2 nested calls also, that also could be a bit complex. But this is just like, if you understood the basics properly, then it will not going to be complex. Actually, it is going to be complex only if you did not understand the basic concepts that we discussed. If there's any issue with that, let me know. So here in this factorial example, you can see adjust the stack for 2 items. Now you have to see what are the 2 items actually that we need to store in the stack. The 2 items, we got that answer from someone. Who was it? Acer and Madhushan. They told us the 2 values that we need to preserve in the stack. So those are the So we have to adjust the stack to store those two items, and return address is 1. That is LR. LR you have to preserve in the stack. STR, LR. So the usual instruction that you are using to preserve value or store value in the memory or stack, to be specific. So LR we are storing it, and then we have to store the argument N as well in the stack. So that we are doing here, and then we have to do this comparison. That is the comparison that we are doing with that if condition in our code. So you have to compare R naught with value 1, right? We had this N smaller than 1 condition. So for that you have to compare R naught with 1, and then if R naught is greater than or equal to 1, you have to go to that else part, right? Where most of the interesting stuff will be happening. You have to go to this part, else part. If BG, if R naught was greater than or equal to 1. Now L1 is here, and L1 inside L1, what we are doing is you have to decrement N, because we are going to perform a nested call with the with N decremented by 1. So that you have to do with this sub instruction. You can do that, and then again you have to branch PL fact. So you will be branching back to factorial, branch and link back to factorial. This is the nested call. And now when you come to this location, you are assuming that like you actually can think that the factorial function is done with it. So there will be a recursion call graph. So you all know that. So anyway, when it comes to this location, now R naught is going to contain the value of factorial n minus 1. N minus 1 factorial will be calculated by this factorial call, and when you come to this point, you can assume that the factorial n minus 1 is calculated, and the result is put back to R naught, because we have the convention that the result value, the return value is put to R naught. So R naught now will contain factorial n minus 1. Now we are not yet done, because we have to multiply the this n minus 1 factorial with n. So this is actually where the actual calculations will happen. And n minus 1 has to be multiplied with n. So we will be, for this purpose, we have to restore the original n into R naught, right? So the original n you have to restore by loading it back into R naught. So we have the return result also in R naught. Since we are going to load or restore the original value n in R naught, the original value also will be stored. Since we are going to restore the original value also in R naught, we have to put the return result into somewhere else. Like we have to move it into some other register, and this some other register we have used here is R12. R12, if you looked at that convention list, you can see that register you don't need to actually preserve. So when you are going, if you are going to use R12 inside a function, you don't need to actually preserve it. So that is why we are using R12. So R12, you can use it for the things like this. Now R naught, you move it to R12, and then LDR R naught SP hash 0. This one we are using it to restore original value n. So we are loading R naught with the original n argument n, and then LR also you have to get it back from the stack. And now since we are done with loading these two values into the original registers, we can now release the stack space by popping. We call this releasing the stack. We call it as popping as well. Now, but pop actually means you assign the value to another register or a variable and releasing the stack space. So it actually means two things, but here that word is used just for this instruction. That's okay. So pop two items from stack or release the stack space that we use by adding stack pointer 8 to the current stack point value, and you can now multiply R0 with R12. R12 is holding the original n value, and R0 now is sorry, R12 is containing the factorial n minus 1 because we moved it to there, and R0 is containing n and n minus 1. You can multiply them, and we are assigning that back in R0. But you have to check this multiply instruction. There was a limitation, if I can remember. This multiply instruction, it cannot have source and destination registers as the same register. That is like you cannot have R0 in source as source and destination. So you can check that. If there's any issue like that, you can change this. Like you can move the you can get the result, like you can move it to somewhere else, something like R1, and then again like do the multiplication with R0 R12 and assign it to something like R1, and then R1 back to R0 by using another move instruction. So that you can do. If I remember correctly, multiply instruction does not support source and destination instructions registers to be the same. Just check it, and if it works, then there's no issue. And then finally you return. And this is the else part actually. Else part, that is if the n is greater than or equal to 1, and if it was not the case, if it is if n was smaller than 1, that is n is 0, all what we are doing is you have to return 1. If n is 0, all you have to do is return 1, and that you can do by moving 1 into R0 and releasing the stack space. Actually, when you come to this point, you will not now here, like inside the if part, not the else part, if part, you are not multiplying 1 with original n or something like that is not there. You just return 1. So that is all what we are doing. But the stack space allocated by the previous call or at the beginning of the factorial function, you have to release it, because at the beginning of factorial function, no matter whether it is whether n is smaller than 1 or greater than 1, we are preserving return address and n in stack. So we allocate space in stack and preserve these things in stack. We just don't check whether R0, like the n is smaller than or greater than 1 at the time we allocate the stack. So if it is smaller than 1 also, you have to release the stack space, because that already has been allocated, even if it is in the if part. Even if you are in the if part of the code and move PCLR, that is okay. So PCLR now is not changed, because when you come to this part, you are not actually doing a nested call. So the LR which is there in the link register, the return value, return address that is there in the LR is the actual return address to which you should return. So that is how it works. And you can actually spend some more time if it was not clear at a class. You can spend some more time and try to understand it. And also it's better, like you can use this visual tool and try to simulate how it happens and how registers are changing their values. And also there's an option to see the memory content in visual. That is also an interesting part. In the visual tool, you can see under tools, I think, yeah, under tools you have this memory contents tool which you can use to see the memory content. So the stack and all that, I was explaining it with the diagram and all. So you can see how memory is actually updated by looking at the memory content. So memory content also you can monitor with the visual tool. And this next exercise is about uh, doing the Fibonacci function using regression. So Fibonacci sequence also, I think you know now, it's also a very common sequence in maths. And Fibonacci sequence can be calculated by like if nth term in the Fibonacci sequence, you can calculate it by adding the two previous numbers in the sequence, that is fn minus 1 and fn minus 2. So those two values, you can add them up to get the nth value in the sequence. So this one you have to implement using recursion and also in assembly. So you should not use iterative approach, right? If you use iterative approach, that is wrong. Wrong meaning you can actually do that. Like if your need is only to calculate the Fibonacci number, of course you can go ahead with the iterative approach, which could be actually faster and resource efficient. But here, this example, like this is like a problem that we are giving to you. So we are having the restriction that you should use only recursion. So use only recursion, don't use the iterative method. So you will have a base condition telling if n is smaller than 2, maybe. Yeah, smaller than 3, if you have to return 1. That's it. And was it clear? Like, was this thing clear? If it was clear to some extent, that's fine. And if it is clear to its like to full extent, that's really fine. And if it was not clear at all, that is not fine. So if it is clear to some extent, you can actually go back and like look at it and see how it works again. Since we covered the basics like properly, and I mean spending a lot of time there, you should be able to understand it. And Fibonacci also, you can try it out on your own. And we have 2 slides about this memory layout and stack. So it's like a review, and that also I'll quickly discuss. And there are some other 2 like examples that you can actually try on your own. The example code is also given. That I'll come after I'm done with this. So if you have any questions, just ask. Just ask, like if it. So far, if you have any questions, you can ask. Or else I'll cover these 2 slides quickly. Now this is actually formally talking about the purpose of stack. Local data on the stack. That is, we are storing local data on the stack, and the data that actually we'll be storing in stack are discussed here. I already talked the high address. The stack point is initialized to the highest address in the memory, and it is going lower from starting from that highest address, and low address is here, high address is here in the memory, and we start with the highest address. And when we get the need of saving argument registers, if there's any, we use the stack arguments if you want to save. And also if you want to save the return address corresponding to the function, we save that as well in the return in the stack. And saved registers. So if you want to save other registers, you can use the stack. And also local arrays and structures also you can store in the stack. So the arrays, actually we discussed about this. We talked about arrays, how you can load values from memory so that was I explained that when it comes to arrays, you have to store those things in the memory, and you have to use these memory operations, memory instructions to store them in the memory and also load them back to registers, all that you can do with str ldr instructions. So we looked at arrays, and actually those arrays, local arrays, are the place where those local arrays are stored is this stack. So stack is the place where we store those arrays in. So you can go back and look at the skeleton codes we have given to you until now, and see that those arrays actually were stored in the stack. So we were decrementing the stack pointer so that it can have all the values in the array. And also once when we are storing and loading, we used the stack pointer. When we are loading, just we use the base address and all that, so that we have discussed. And once we are done with the array, we release the stack space we used to store the array. So that also was done in the example skeleton codes given to you, but you were not focusing on that part earlier. But now you can go and check those things. So arrays are also local arrays are stored in and structures are stored in the same stack. So local data allocated by Kohli. So Kohli is the function that is being called. So those local data are going to be stored in the stack. And in C automatic variables, that is like inside C you define variables. A equals 10, B equals 20, and things like that you declare in C code, C functions, actually inside C functions. So those variables are stored in stack. If the processor, if the registers are not enough to store all those things, which is the case most of the times, so those values are stored in stack. And when the function when the program returns from that function, the values in the stack are released. About output, the stack space is released. And this stack frame or activation record is a segment of the stack containing a functions, saved registers, and local variables. So this is like a stack frame where we have stored all the values corresponding to that function. So arguments and return addresses and all that we store. And if there's a nested call, actually we will be using stack further to variables and other things required for nested function calls. So stack pointer will be decremented, and when you call functions in a nested way, actually when it comes to recursion, you will be calling a lot of you will be having a lot of nested function calls inside a function. Again, you are calling the same function again and again. So that will increase the stack space used. So that is stack point actually is going to be decreased further and further. So if it is a nested call, like if it is just the first function call, you will be decrement the stack pointer to save all the values that you need to have, the link register and all that. You will be backing them up in the stack, and then inside the nested function call, the second function, you will be decrementing the stack pointer further and storing the values required in that particular function. And when you return from that nested function, you will be releasing that space used for that nested function, and will be coming back to this place in the stack inside the first function, and it will be consuming the value saved in the stack again, and return from the function to the main code. So that is how stack works, and this is the reason actually to have a structure like this to store the temporary values used in functions. So when it comes to function calling, the stack becomes really important, and that is one of the main reasons to have a stack structure, stack concept in the memory. So first in, last out data, last in, first out data structure. You can call it the other way as well, but last in, first out. Segment of the stack containing a function, saved registers and local variables. We call it the stack frame. So this one, and that's it. And if you look at the memory layout, the full memory layout, stack is only a part of that, right? There are other things as well in the memory, which we are using for other purposes. And stack we already have discussed. And the memory actually you can divide into these segments. You can look at this. This is like an overview of the memory as divided into separate parts, and at the top you have the stack, and actually this top part, this segment is shared by stack and the heap. So there's another part in memory called heap. Heap, have you come across that term, heap? When you used the dynamic allocations in C programs, maybe you were told that you are storing those things in the heap. Maybe you have been told, but that doesn't matter. So stack and heap, we call it. The stack actually, heap for now, maybe ignore. Stack and static data section is there in the memory, and also text segment in the memory, and also there's a reserved part. So this text part in the memory, that part is used to store the program code. So our program code or the instructions actually are stored in this part of the memory, text part. And the static data, they are the global variables, static variables that you have seen in C. Also strings, those are constant values that are common to the full program. So static variables, global variables that are common to all the functions and all the full program, those data, we are storing it in this part of the memory. Static variables, I think you have seen in C. So those things by the compiler are going to be stored in the static data section in the memory. And this stack or the dynamic data part, and now we come to the heap, dynamic data. It is heap, and this part actually we are using it to allocate memory in cases like malloc in C. So malloc, you have discussed about malloc IGOs in C. So I think when you do a malloc, the memory allocated using malloc is not going to be contiguous in the memory. So that is, you can allocate at any place in the memory using malloc. And the memory allocated by these malloc and new in Java, that memory is going to be stored in that data is going to be stored in the dynamic data part, and that part actually goes from a lower address to higher address, lower address to the higher address, and the stack and heap are going to be in the same portion, but stack goes from the higher address to the lower address, heap goes from lower address to the higher address. So stack is the main part of our interest when it comes to function calling and these local variables. When it comes to malloc and things like new in Java, you use this heap. So stack, it is an automatic storage like we discussed earlier. When it needs to store something when it needs to temporary value in some random memory, it is using stack. So when it returns from the function, stack is released. So when you return from the function, you don't have the reference to the address or the value that you stored in the stack, because once you are done with the stack, you are done. So you can't go and check the value stored in the stack by the previous function. But with heap or dynamic data, you can keep track of the memory across functions. So that I think you have already looked at. So that is not an automatic storage. You allocate, and you can free that memory only by using another function, something like free in C. When you say free, the OS goes and free the memory allocated by the malloc function. So that is how the heap works. But stack is an automatic storage. When you are done with the function, you automatically release that space used for the function. And how it is, how it should be like when it comes to C, the compiler does that job. It compiles so that the stack is handled properly. You allocate space in stack, and when it calls a function, it allocates the instructions needed to allocate the stack and store values in the stack. So all these things are done by the compiler, and it generates the assembly. But if you are doing the program with assembly, you have to do that yourself, allocating space in stack and storing values in stack and restoring values to registers. All that you have to do it yourself. If you don't do it properly, then you get into trouble and you get errors like stack overflow, things like that you are getting, because like when you are trying to access a place in stack that is not allocated for your program, you are getting those errors. So you have to carefully handle the stack when you are doing it with C, assembly. Hope that was clear and you got some idea, got a good idea about stack and how you can do the function calling. And again, you have another like a bigger example. We can call it a sort example, how you can do sorting with C. That is like how to write a function to sort an array using C, and that is actually a part of the program only. This first part is about the swap function you use to swap two values. When I think you have discussed about bubble sort in your C course, and inside the bubble sort you get the need of using this swap function, and that is first thing implemented. The example code is also given here, and there are things, assembly directives that you can use to rename a register value to something else. And if you are not clear about those things, you can ask me. And then sort function is there to sort the values. Inside the sort function, you are of course going to use this swap function. So here also you will be using nested calls, because sort is the main function, and inside the main sort function, sort actually not the main function you have somewhere else, main function, the main program you have, inside the main program you are calling the sort function, and inside the sort function you are calling swap function, which is a nested call. And so when it comes to nested calls, you have to make sure that you preserve link register and arguments if needed in the stack. Yeah, that is it. So you can have a look at it. Have a look at this sort example yourself, because the basic examples that you need to know, we already discussed them. And any questions? We are done actually with function calling. Any questions? Was it clear anyway? Did you get an idea about how we do the function calling? That is the lab actually. You have to compile a function call, nested function call, I guess. You can start working on the lab now. Okay, all good, I guess. So if you have any questions, use the forum or the chat.